Alright, so calculus lesson 2 notes. We're going to be dealing with a lot of inequalities today and intervals of inequalities and how to solve for them. Remember 1, 2, 3, 4, 5 from Monday through Friday. If we get ahead and say we need to do another set of notes on Thursday, then Thursday when you come into class I'll tell you, hey, you need to do 4 and 5. Alright? So looking at example number 1, we need to write an inequality to represent each interval and state whether the interval is bounded or unbounded. Okay? Well, when you have something like this, the left side and this mark means it's less than, whereas the right side is closing it off. It's greater than, but boxed means equal to, and we just put our variable in the middle, and our variable will be x. Okay? Now, because it is closed on both ends, this is a bounded interval. Now, looking at example B here, we're saying that -3 is less than the value of x, but x goes to all real numbers from that point. So x is not going, we're not going to say x is less than infinity. X is going to be all real numbers up to infinity, so we're just going to say that this is an unbounded interval. Okay? Now, just by guessing, you're probably looking at C and saying, okay, so this one's bounded and D is unbounded. If you say that, you're probably right. Now, remember, this symbol means less than or equal to the value of x, which is less than or equal to the value of 2, and it is bounded. And then finally we have, how do we want to write this one? Let's go ahead and do it like this to show that negative infinity is less than x, but x is less than infinity. Okay? And that just tells us that we go to all real numbers without writing it down in words. So from here we can say that it is an unbounded, completely unbounded. And I switched my B and D, sorry about that. So don't write unbounded, write unbounded. Now, example number 2, we're going to solve linear inequalities. Basically, we're going to solve this as though the less than or equal to sign, or greater than or equal to sign, or less than or greater than sign are an equal sign. And all we're going to do is move our components back and forth so that we can combine like terms. I'm going to start by subtracting 3x from both sides so that I can rewrite this as 2x minus 7 has to be greater than 9. Alright, now I'm going to add 7 to both sides, and it's going to change to 2x must be greater than 16. And then I can divide by 2 sides, so x is greater than 8. Alright? Not too terribly difficult. Solving for a single linear equation, not bad at all. Alright? So a little bit more complicated single linear equation, or inequality, I shouldn't say equation, inequality. Let me move this down. We're looking at doing the same thing as far as combining like terms. So I'm going to, which way would be easier for me to start with this one? You know what, let's make this real easy, and let's start by multiplying the entire problem by 2. That way I can get rid of that divisible 2 right there. So if I multiply the entire problem by 2, I'm going to change it to 2 minus 3x is greater than or equal to 2x minus 8. Fair enough? Alright, now from here let's go ahead and combine those 2's. So I'm going to combine those x's. I'm going to subtract 2x from both sides so that 2 minus 5x has to be greater than or equal to a -8. Then I'm going to subtract 2 from both sides, And I should wind up with a negative 5x is greater than or equal to a negative 10. Now at this point I have to divide by a negative. Anytime you divide or multiply by a negative, your sign will flip. So instead of x being greater than or equal to, x is now less than or equal to a positive 2. I had to think about it for a minute. Alrighty. So remember, from this step to this step, flip sign. And we're doing that because we are dividing by a negative. If we were multiplying by a negative, we could do the same. Okay? Let's go to example number 4 real quick. Example number 4, we have a double inequality, which means we have values of x on both, or we have values on both sides. This is a bounded inequality. Okay? So when we do this, our first step is to isolate the x. Well, when I add 1 to get rid of it, I have to add 1 to this side as well as this side. The whole thing has to be changed. I have to treat it as 3 separate parts. Okay? So negative 3 plus 1 is going to change to negative 2 is less than or equal to 6x, which is less than 4. From here, I need to divide by 6. Now, remember in the other one we flipped when we divided? We only flipped when we divided because it was dividing by a negative. Here, we're not dividing by a negative. So, this will become x, and x will be less than 4/6 changes to 2/3, reduced. Negative 2 over 6 or 2 over 6 changes to 1/3, and we're going to keep our negative. So our interval is bounded between negative 1/3 and positive 2/3. Now the negative 1/3 is included, and the 2/3 is not. So if I were to graph this, do something like this. Draw my number line. I'm just going to put negative 1/3 here. I'm going to put 0, and I'm going to put a positive 2/3 here. So I would curve it 2/3, and I would box at negative 1/3, and then I darken the line to show that all of these between are counted. Alright, so example number 5, not too terrible. We're just looking at the absolute value. The absolute value, remember how we did it in the last one, you have a positive and a negative. Okay? You're going to wind up having a bounded solution or a solution that works outside the bounds, depending on how it function tests. Okay? So, let's look at this. X minus 5 is greater than or less than 2. Okay? So I'm going to start with x minus 5 less than 2, and then I'm going to come over here and I'm going to make my second one, and I'm going to call it negative x plus 5 less than 2. Make sense? Remember how we have to manipulate both sides of it? Okay? Now, we can do this and solve for x individually. So add 5 here and subtract 5 here. So I'm going to wind up with x less than 7 and a negative x less than a negative 3. Now here I still have another step. I need to make that positive. Well, when I multiply the entire problem by a negative 1, I'm going to change my sign so that x must be greater than 3. Okay? So, when I'm looking at this, I can combine these two so that they read x in the middle, x is greater than 3, but x is less than 7. Okay? I know this probably combining these two things is probably going to be the hardest step for you guys. Alright? Now let's look at the other one. The negative 7, or I'm sorry, the x plus 3 greater than or equal to 7. So Again, we're going to write 1 as x plus 3 greater than or equal to 7. We're going to write the other one. Let me draw a little line right here. So I've got A up here for you guys, and I've got B down here. And then on the other one, we'll go a negative x minus 3 less than 7. Okay? So I'm going to start by subtracting 3 over here so that x is greater than or equal to 4. And then we're going to add 3. And that's going to change to a negative x greater than or equal to 10. And then we're going to multiply by the negative 1. So we're going to change our value so that x is less than or equal to a negative 10. So now we have two separate ended equations, which means we're going to work away from the bounds. So that if I was graphing B, I'm going to write over here and I'm going to graph B for you guys. If I was graphing B, I would say it so that the only 2 points on here that are going to be important are negative 10 and positive 4. Okay? Negative 10 is included, right? And positive 4 is included. Now you may be wondering why I put the boxes away from each other. Well, if I look at this, x is greater than 4 and x is less than 10. So if I was looking at what it couldn't be, it would be everything in here. This is a no solution area, whereas the solutions to make this true will be on either side of negative 10 and positive 4, as well as including those. Alrighty? Awesome. So your final example right here, guys, is to grab a partner and create a linear function. 3x plus 5, or 3, like example 3x plus 10, or negative 2x plus 2. And once you both have your functions, you're going to write a composition of your functions. If you need help, you need to look at example number 3 in the pre-calculus book, section 1.2. But let me work out the example. We're going to use these two, here and here. Okay? We're going to say that f of x, my function f of x, is equal to 3x plus 10. And we're going to say that the function f, or g of x, two separate functions, is equal to the negative 2x plus 2. Now, here's a composition, or here's what a composition writes. The function of f of g. Okay? What that tells me is insert g into f. So then what I do is I write f, and what was f? Okay, f was 3x plus 10. Now what are we putting into x? We are putting negative 2x plus 2. So I'd come over here and put negative 2x plus 2, so that I'd have to rewrite this as 3 times a negative 2x plus 2, close the parentheses, plus 10. FOIL out and combine like terms here, so I'd wind up with negative 6x plus 6 plus 10. My final answer for g, or f of g, would be negative 6x plus 16. Now, that's the first composition of this function. The second composition of this function is written in the exact opposite, and it would say g insert f. So I'd start with g here, open those parentheses up, and g originally is equal to negative 2x plus 2. Well, I need to insert f, so right here I'm putting 3x plus 10. So when I rewrite this, I rewrite it so that negative 2, open parentheses, 3x plus 10, close parentheses, plus 2. And then FOIL out, and I'd wind up with negative 6x minus 20 plus 2. And then combine my like terms, so this would finally equal negative 6x minus 18. Okay? So this is g insert f, and this is f insert g. They'll be slightly different when you do this, and you need to do both. Consider yourself F and your partner G when you're doing this. Alright guys, see you in class Tuesday with all the work done.